The second problem is going to be a lot like the first problem, but we have different numbers, and if you follow the same procedure, it should be faster. So I'm going to remind you that I've given you a formula that I like to call PERT. Looks like this. Here's the PERT part. Starting population, exponential for continuous pounding, rate of growth, time of growth, and it will all equal your final population. Now, how do we apply this here? Well, it says a bacteria culture grows, and that's a big shocker. But what they did for us is they measured that 2 hours after it started, the population was 400, and after 6 hours, it was 25,600. So they give you a couple points of data with which to discern the relative growth rate. So how do you think we should go about doing this? Well, it seems to me that if we have a growth model, then we know it's something like a plug and play. Let's do the first one first. So I'm going to say 400 is our population equals some unknown P, E to the R, and then this would be 2 hours. And another thing we know is that 25,600 equals some starting population, E to the R, and then we have 6 hours. Does this make sense to me? I think this makes sense to me. So maybe we can just divide them by each other. So I would say 25,600 divided by 400. We'll just cross those off now. What's 256 divided by 4? 128, so it would be 64 equals P naught E to the 6R divided by P naught E to the 2R. That means the P naughts cancel. So we could say 64 equals E to the 6R times E to the negative 2R. See, I brought it up from the denominator. It's still algebra. We haven't done any calculus. So remember what I say, 90% of my students who fail calculus is because they're bad at algebra and they thought they were hot. Well, these will just add. So 64 equals, this looks like it's going to work, E to the 4R. Well, what do we do when we have a variable in the exponent? I've said it every time. We take the natural log. This is still algebra. So ln of 64, you're going to find this is almost always all algebra, equals ln of e to the 4r, which allows us to take the exponent out and bring it down. So we have ln 64 equals 4r ln of e. And ln of e is 1, so just divide this by 4 and you get r. And that's going to be, let me put it in the little calculator machine here, we're going to get r equals 1.04. I'm rounding, but this is good enough for us. So here's our relative growth rate. This is what they want for r here. That will give us that. So as a percentage, that would be 104%. That's what they want, is it's expressed as a percentage. Then they say, what's the initial size of the culture? Well, we know I'm going to erase some of this now because we've done some of this work, and I'm just going to bring the r up now that we've solved it. We'll say r equals 1.0. I'm just going to say 397 to keep it as accurate as possible, but 104%. Let's put it in the easy one here. Let's say 400 equals our unknown start, e times 1.0397 times 2. Well, we can just divide the e out, put e to that exponent and then divide it out of 400, and I'm going to find that P naught is going to be something like 50. I want to say I got 50.03, but you can't have 0.03 bacteria, so we'll say 50. That makes sense to me. Now, what do they want? They say Find an expression for the number of bacteria after t hours. Well, we have everything we need for that because it's p of t. Remember, they're asking for the PERT formula. That's going to be 50 e to the 1.04 t. Obviously, I'm doing the rounding for you because it's good enough. At least in my class, it sure is. If you know the math, you can show me the math. The decimal is going to be unimportant. Your calculator can handle that. Now there's our expression. And they come down to part D and say, find the number of cells after 4.5 hours. Well, I don't even have to tell you how to do that. Just put 4.5 in for T and put it in your calculator. The answer that I got for that was 5,392. I want you to notice how fast that is with a growth rate of 1.0. Not really a big number, it seems. 50 bacteria become 5,000 bacteria in 4.5 hours. That's real life stuff right there too. That's not messing around. Then it says find the rate of growth after 4.5 hours. And you might say, hey Blake, isn't this the rate of growth? We say no. That's the relative rate of growth. That's the instantaneous compound interest version of the rate of growth. If you want the real rate of growth, you need to take the derivative. So what's the derivative of p of t? P prime of t is 50. What's the derivative of e to the x? It's e to the x. But the chain rule says also times 1.04 out here, right? So then we can put in t. I hope you're with me so far. And they want the rate of growth for that same time period, 4.5 hours. So put 4.5 in for t. And what do you get here? I got about 5,606 cells per hour. Which means if you're looking at the growth at that exact moment, notice its growth rate is just a little higher than its population, which makes sense from the relative growth rate. Now this is like, you can think of this as the nominal amount, and you can think of this as almost like the percentage it's compounding by. So it should be just a little bigger because it's 104% growth. Okay. So what do we have left? What does it want left? When will the population reach 50,000? Well, that's this P of T here, right? So 50,000 population equals a starting population of 50 times e to the 1.04 t. Divide the 50 out. This becomes 1,000 equals e to the 1.04 t. How do I get the t out of the exponent? You better know by now, or Blake the tutor is going to be upset. Natural log of 1,000 equals natural log of e to the 1.04 t. Bring the exponent out of the natural log. Obviously, ln of 1,000 equals 1.04 t. ln of e, what's the natural log of e? That's 1, so that's gone. Divide by 1.04. I'm not using the full decimal, right? You can do that on your own. And I'm going to get t equals ln of 1,000 divided by 1.0, whatever the real long decimal for that was. But I tell you what I'm going to get is something like 6.64 hours. So you should come to this answer here. And if you were able to follow that, then that's 2 bacteria examples. I think by the time we're done with 8, you're going to be crushing it. Let's move to the next one.